All right, everybody. So first off, announcement, good news, especially for everybody on the wait list. It might require a little bit of juggling of schedules, but I was able to convince admin to add another lab section. It'll be Thursday from 1 to 4. So anybody who is still on the wait list and can make that time work will be able to add that time slot. So we'll be able to get you added to this class. And so nobody's out of luck this term unless you have some other class that you can't work around. It's already scheduled at that time slot. Again, it's Thursday 1 to 4. Anybody in any of the other lab sections, either the other lab sections, if Thursday afternoon works better for you, I highly recommend moving to that lab section because it's not going to be as full, and lab sections at the end of the week that aren't as full tend to go faster and more smoothly because I've already done it with 2 other groups of students by then. And the more crowded a lab section is, the less time I have to help all of you individually. So if you can make that work, it's to everybody's benefit to switch to that, not obviously all 50 of you. I don't want 50 of you trying to switch into Thursday lab section, but if you have that time slot open, something to consider, you wouldn't have to re-register. I can do an instructor switch that just where I go to student services, fill out a piece of paper and move you over. So it's no extra work on your end. So let me know if you're interested in that. And if you are still waitlisted trying to add this class, by the end of the day today, that lab section should be available. But I think we have to do something because it's technically a late start class. They have to do something funny with the records to do it. So it might not show up as being able to register directly. But we'll get that sorted out by, if not the end of the day today, then I'll have, check your email tomorrow, for information from me to get registered officially before that census date on Friday. So again, and anybody, it's open to anybody, it's not just the waitlisted students. I know everybody already has their schedule set, but I highly recommend if you have that time slot, thinking about switching over to that Thursday lab. At the very least, it gives everybody a lab. And you can't come to the Monday lab section. That gives us an option. If you can make Thursday work, you can come in Thursday if you have some conflict on Monday or something like that. So good news all around on that front. Any questions about scheduling issues? Awesome. I see most of my waitlisted students are here, so that's good. I really don't want to do this and when use up my chits with the admin if a bunch of people are then going to drop, but all my waitlist students seem to be continuously showing up and asking to still be in the class. So should work out well for everybody. All right. Some random questions. How does sourdough work? What makes it sour? Anybody know? How do you make a sourdough starter? Anybody do that over COVID? Anybody's parents? Yeast? Technically, to make a sourdough, to make a really good sourdough, you don't even need yeast. If you're making your own sourdough at home, usually you just make a dough and you just leave it out on your counter for a little bit and you let the natural microbes in your house start to colonize it. And so that's actually what makes it sour is it's not just yeast. There's yeast on pretty much everything, wild yeast. But what makes it a sourdough is usually that there's other bacteria, there's other microbes, most significantly lactobacillus, and they produce other byproducts. When yeast breaks down sugar, it turns it into CO2 and water, or sorry, CO2 and ethanol, alcohol for the most part, depending on the conditions. And that's what makes bread rise, is that CO2 fills in those little pockets of gluten that you make when you make a dough. Gluten is just a protein that happens when you have certain proteins and you add water and you mix them together, you get this like mesh of proteins. It kind of is small enough that it actually traps air. And so that's what causes bread to rise is when yeast produces CO2 and fills those little pockets and they expand. If you have other microbes as well, they don't just make ethanol and CO2 when they break down sugar, they also make stuff like lactic acid. In most acids taste sour. That is what a sour taste in your mouth actually is usually means you're tasting something acidic. So any sort of fermentation process that produces an acid, usually it's lactic acid, but there's other stuff as well, will give you sort of that sour taste to it. And that's why sourdoughs from different parts of the world are going to taste different because they have different ratios of those microbes already present in the air. So you're going to get different amounts of sourness and different notes depending on what those microbes are. They're also usually the same microbes that you use to make a sour beer. So lactobacillus is the most common one, makes a nice clean flavor where you basically just taste a little bit of tartness. But if you've ever had, I don't know how many of you are 21 or into sour beers, but if you've ever had a Brettanomyces sour beer, Brettanomyces makes all of these weird compounds in the fermentation process that kind of taste, sometimes people describe it as tasting like leather. Like the way that leather smells is the way this beer tastes sometimes. Some people describe it as it tastes like a barnyard smells. It doesn't sound particularly attractive in most cases. It's a very acquired taste. It's not for everybody. I don't particularly like them myself, but if you want to why different sourdoughs and different sour beers taste different, it's because they have those different microbes present, because different climates create different strains of these bacteria and other microbes. This is an easy one. How come black holes have such a huge gravitational pull? Because they're really big. They're really heavy. There's a lot of stuff in there. So they have a lot of gravity. Gravity is just the attraction between two things that have mass. You have a whole bunch of mass, you have a whole bunch of gravity. It's just what makes black holes so unique is that they have so much mass in such a small area that not even light can get away from it. Light, depending on what assumptions you're making, has mass to some extent. It doesn't really have mass, but it has momentum, which is a function of mass. So it acts like it has mass, even though it doesn't. Physics is weird. Quantum is weird. We'll get into light in more detail when we talk about quantum. But basically, you can have these photons that can't get away from something just because it's so heavy. Just like if you had a really exceptionally strong magnet stuck to your fridge, you can't pick it up, you can't pull it off the fridge. You can imagine something that's so heavy that the lightest particle known to man basically can't be pulled away from it. That's all a black hole is. It's just really heavy. Another beer one. You all already figured out how to get me talking about random stuff. Food and beer. Why does beer taste better when it's cold? Turns out your taste receptors work best around room temperature. You get stuff really, really cold, your taste receptors aren't as effective. And so basically beer tastes better when it's cold because you don't taste it as much, especially cheap beer. Cheap beer is like, if you look at, Coors Light commercials and Bud Light commercials and stuff like that, cheap beer is designed to be drank as cold as possible so that you taste it as little as possible. Basically. And nicer beers typically actually taste okay at closer to room temperature. If you buy good beer, it doesn't have to be that cold. In fact, if you really like getting all of the notes, if you're a person who really likes trying to taste everything in a beer, then you actually don't want to drink it cold. You want to drink it 50 degrees to 70 degrees Fahrenheit. Which is also why you do wine tastings. You don't refrigerate red wine because you're supposed to be able to taste all of those things. And you taste them better when it's a little warmer. More refreshing when it's cold, though. I will admit that. Speaking of cold, why is it the water freezes? Why does it expand when it freezes? This is a good everyday question. We're going to talk a lot about phase change towards the end of this term. Basically, crystalline water, which is ice, it has sort of dead space in between the molecules. The molecules in a water crystal are arranged in such a way so the hydrogens are all pointed towards other oxygens, and you get this sort of cool lattice structure. But it inherently has an empty space in it. And that's basically just an artifact of the way that in order to get everything oriented just so. Thanks. Let me pull up a picture of it. Yeah, there we go. So there's a lot of different ways you can arrange it. This is a decent one. You can see the reds are oxygen and the yellow is hydrogen, which is weird because hydrogens usually are white. But you can see that when it's arranged just so, you have sort of these empty spaces in between the water molecules. When it's a liquid, things are moving around more, and that empty space gets filled in a little bit more. So even though it's more organized when it's a crystal, it actually takes up more space because the crystal structure itself has empty space in it. And it turns out most things, when you put them into a crystal structure, get more dense. They get better at packing together. Water is sort of the exception, partly because it makes these hexagonal crystal structures like that. And it turns out the ice we're used to that expands when you compress it or when you freeze it is not the most dense form of ice. There's actually other ice crystal structures that are more dense. If you put water under a huge amount of pressure, like the center of a gas giant levels of pressure, you can actually get it more dense than liquid water, more dense than this. So when we talk about how ice is less dense than water, how it expands when it freezes, we're really specifically talking about on Earth. That's an example of what there are a few properties that we'll talk about in this class that are specific to Earth. We think of them as being fairly universal, but that's just because, we're on Earth. Every human that's ever lived has spent almost all of their time on Earth. So why wouldn't we design our chemistry periodic table and things like that around the properties of Earth? But for instance, if we went to, if we were on a different planet, even in our solar system, we could have a different periodic table to some extent. All the elements would still be in the same spot, and we'll talk about why next week. But the mass numbers would be a little bit different if you're on different planets, because we'd have different ratios of specific isotopes of those elements, which is kind of interesting. I think it's kind of fun to think about what chemistry would be like on other planets. Turns out it's mostly the same. And then speaking of other planets, do I believe in aliens? I think that there's a pretty good chance that there is life other places. Is it going to look like humans? Probably not. Probably not anything like humans. Will we ever be able to make contact with that life? Probably not. Turns out space is really, really big with lots and lots of galaxies and lots of suns and planets and things like that. Lots of chances for life to evolve. But they're all really, really far apart. Given our current technology, it can take anywhere from 8 months to 3 years just to get to Mars, which is one of the closest planets to us, right? Getting to another solar system, technically they're not called solar systems. Getting to another planetary system is gonna, even if you're moving the speed of light, we're talking about like a 4-year travel to get to the closest planetary system to us. So it's never going to be easy to travel. And if life evolved on the opposite side of the Milky Way, it could take, I want to say it's like 100,000 light years across the Milky Way. It could take tens of thousands of years just for a radio signal from that other system to reach us, which doesn't exactly make for a great conversation. By the time we were evolved and started looking for those radio signals, that other civilization might have gone extinct. So the odds are we'll never actually make contact, right? But the odds are also that the life is probably there. Who knows what will happen in the future? That's all just with current technology. Get really weird stuff like wormholes and things like that. Who knows what could happen But that's all sci-fi at this point. That's not real science. It's all speculation. All right, fun random questions, right? Couple minutes. Let's do some practice with scientific notation. Let's start with just if I give you some numbers, write them in scientific notation. Just do some practice. The exponent, right? The power, right? Positive versus negative, right? This is a little warm up. Camera.
You got it. You got it right, I got it.
So common thing when you're dealing with small numbers. So one of the reasons why we put these commas in there is so that you can count from across the room, right? And do it in groups of 3 for a reason, because we think in threes. So 10 to the 5, 3, 6, 9, 12, 13. 4.07 times 10 to the 13 kilometers. What you commonly see in textbooks for small numbers, we don't usually put commas behind the decimal point, but we still need a way to easily count if we have a whole bunch of zeros on a small number. So what you'll frequently see in textbooks is just a space in the middle. That's basically, they do it every 3 digits, the same way that you do with a comma, but it's behind the decimal point. It does make it still not easy to see. So sometimes what I'll do is I'll use an underscore to show you that there's a space there. How's that looking? How do I know where to stop writing digits? Why did I stop at that 9 and not write zeros there?
The 2 trailing zeros are not.
Technically, I'm guessing. Because if I don't know what the uncertainty is here, it might be 997,900 feet plus or minus 1 foot. The uncertainty could be in the ones place here. It's unlikely. Usually with really big numbers, when we stop seeing digits like this, that means that they're not measured numbers anymore. They're not sig figs. But these first 2 are what are called ambiguous numbers. So my students from lab on Monday heard that term in lab. Ambiguous just means you don't know how many sig figs it is. Is this 3 sig figs or 4 or 5 or 13? Technically, we don't know. So we have to assume the fewest possible sig figs. You have to assume that the number is as bad as it could be if you don't know otherwise. Right, so we stop there just because we're assuming that these zeros weren't measured. And that's one of the reasons to use scientific notation. We didn't really save any space by using scientific notation with this number, right? It's about the same number of things to write. But what we gain from that is we can be really explicit about the fact it's 4 sig figs. And if it's 4 sig figs, where's the uncertainty on that first digit, on that first number? Where is the estimated number? That last 9. Right there. So if we're assuming that that's the last measured number, that's where the uncertainty is, which means we could be plus or minus 100 feet. If we wanted to write the uncertainty, we would write it like that. So it'd be plus or minus, you could write plus or minus 100 feet. Then it doesn't really match though. It's a little bit harder to see. You could also write it as 9.979 times 10 to the 5 feet plus or minus 0.001 times 10 to the 5. Doesn't like when I write on the very edge of the board. Pretend I wrote a 5 there. It's a little bit harder to see what that's actually telling you. This is the downfall of scientific notation. For most things, when you get used to it, scientific notation is actually way easier to understand and do math with. Other than being able to think about what the uncertainty is. It's a lot easier to think about this, plus or minus 100 feet, than it is thinking about plus or minus 0.001 times 10 to the 5 feet, which is 100 feet, but it's just a little bit harder to wrap your head around. What's our uncertainty on number 2 then? That last digit that's written, right? It might be one of these other zeros, but we don't know. So we have to assume it's the where the 7 is. Right? We don't get to assume numbers are better than they are. We'd rather err on the side of caution and assume numbers are worse than they are. If somebody took this number and they really wanted us to actually know that that was a significant figure, they should have written it in scientific notation in the first place. So it's plus or minus 1 digit in that place that has the 7. So that makes it plus or minus 100 trillion. There's a million, yeah, plus or minus 100 billion. It's a lot of uncertainty, right? Anybody know what the nearest star is? Trick question, is the sun, but other than the sun, Bruce likes to do that question, trick people. The nearest star that's not the sun, I think, is Sirius. The nearest planetary system that we're aware of that's not the sun, I believe, is Alpha Centauri. Not an astronomer. You should ask Kathy or take astronomy class if you want to know for sure. All right, we're going the other direction. We're still just counting so that we put the decimal place, so that we only have 1 digit left of the decimal place. So in order to do that, we have to move it 4 spots. And it's a small number, so it's going to be 10 to the minus 4. Where's our uncertainty here? The other way of saying is what's the precision? Plus or minus 0.00001. So you could also say plus or minus 1 times 10 to the minus 6. All right, how do we feel about scientific notation? It's a pain at this point, but it's not too tricky. What I'm going for, I'll make the case that scientific notation is not a pain as we continue on. One point I will make when you're doing math with scientific notation on your calculator, like I said, most of your calculators use that shorthand, where they would write this number. If you actually got this number out of a calculation, it would, your calculator will write as 4.07, and then a whole bunch of other digits, perhaps e plus 13. Don't lose that e. Every single year, I have people that will just write the answer is 4.07. And it's always at the very end of the line, so it's easy to miss. Make sure you don't miss that e value. That's one of the reasons why we do that reasonableness check. So that if you get a number, if you just get 4 and you know it should be something in the trillions, go back and double check your calculator and make sure you didn't miss where it wrote e. TI-83s are the worst for that because it blends right in and looks just like all the digits and it's right in the middle of the answer. Well, not the end of that answer. It's really easy to miss it. So just pay attention to that. All right, here's one place where scientific notation is really helpful. It's getting rough ideas of what a number is in your head. If we know the diameter of the sun is 1.4 times 10 to the 1.39 times 10 to the 6 kilometers. We know the diameter of Earth is 1.27 times 10 to the 4 kilometers. How much bigger is the sun than the Earth? How'd you get there? 10 squared. These numbers are pretty close to each other, right? So for the sake of doing math in our head, let's just say that they are the same. Or even just call them both 1. I mean, don't tell the math teachers that I told you could do that, but if you're doing math in your head, that's totally acceptable. If we just want to do a reasonableness check. 1.1 divided by 1 is 1, right? Then if we look at the powers, we get 10 to the 6 divided by 10 to the 4. Leaves us with 10 to the 2, right? What's 10 to the 2? 100. It's roughly 100 times larger. There's no sig figs associated with that because we just made that assumption that those are the same number when they're not the same number. But as far as just getting a rough idea of what the answer is, we should be able to look at this. If we actually wanted to then plug it into our calculator, I don't know what the coefficient's going to be. It's going to be close to 1, but I know it's going to be to the times 10 to the 2. So I know it's roughly 100 times larger. And so scientific notation, it makes it really easy to do those reasonableness checks when you're doing multiplication and division, because all you really need to look at is the powers in order to know if your answer is going to be really big or really small. All right, how are we feeling about that? Ready to do more stuff? Let's figure out how to do more rounding. All right, so I mentioned this at the end of class on Monday, and then Monday's lab got some practice with these rules when it comes to rounding. The reason we're tracking uncertainty in sig figs is because that's going to be what helps us know where to stop writing down digits when we're writing down numbers off of our calculator. Right, so keeping track of the number of significant figures is going to be what allows us to know where to round. But just as an example, if we have something that's 2 sig figs, we have 3.0 times 10 to the 2 inches. If something's 300 inches, plus or minus 10 inches, that's not that good of a number, right? That's not a very precise number. You could be off by a fair bit. Compared to if I actually took the time to measure that same object and I measured it at 301.24 inches. It's a way more precise number. That's got a precision of 0.01. It could only be off, what I'm saying by writing all those digits is I'm off by at most 1/100th of an inch. Which of those is a better number? For if we're gonna actually do measurements, we'd assume two, right? Assuming that I measured properly. Somebody has to go to a lot more work to measure something plus or minus 1/100th of an inch compared to just eyeballing something, saying, oh, the distance these two desks put together is roughly 300 inches. I didn't put much effort into that, did I? It's also not a very precise number. In fact, I don't even know if I would say it's plus or minus 10 inches. It might be plus or minus 100 inches. What does 300 inches look like? Guesses? Oh, you can do better than that. How tall is somebody if they're 6 feet tall? 72 inches. 12 times 7, right? We're gonna do more conversions today too. But so these desks are roughly 6 feet. So 2 desks is probably 12 feet. So yeah, I am probably off by a couple hundred inches. If I said that these 2 desks next to each other are 300 inches. Takes a lot more work to get a more precise number usually. So we want to keep all the digits that we can when we do math with these. If somebody goes to the trouble of measuring out 5 sig figs, that's a pretty precise measurement. That's going to take more work to get that number. So we want to keep as much of it as we can. When we're adding and subtracting, the easiest way to think about it is we just look at uncertainties when we're talking about addition and subtraction. And because that's the example I used where your friend's driving up from the Bay Area and they call to let you know that they got stopped at the light in Placerville and they're gonna be 15 seconds late. That doesn't make any sense, right? Because the uncertainty of their arrival time was already greater than that. And so whatever your uncertainty is, when we're adding 2 numbers, like 2 times, it's gonna take me 4 hours and 15 minutes. And the uncertainty there, let's call it 4 hours and 10 minutes. So we can say it's plus or minus 10 minutes. It's 4 hours and 10 minutes, plus or minus 10 minutes. And I'm gonna add another time to that. See, 4 hours and 10 minutes is 60 times 4, so 250 minutes, right? Plus or minus 10 minutes. We're gonna add 10 seconds. Let's call it 30 seconds. It's a long life class sometimes. Plus 30 seconds plus 0.5 minutes plus or minus 0.1 minutes. If I just plug this into the calculator, I'm going to get 250.5, right? But if my uncertainty on this first digit is plus or minus 10 minutes, my answer's got to be plus or minus 10 minutes. Makes sense, right? If my first number could be off by as much as 10 minutes, my last number could be off by as much as 10 minutes. So when you're adding or subtracting numbers, you're only going to be looking at uncertainties. And whatever is the least certain number, that's the same uncertainty that you want to keep on your final answer. Which means in this case, we're going to round to the 10th place. So it's still going to be 250 minutes plus or minus 10 minutes. Or to avoid writing an ambiguous, technically, if you write the uncertainty, this isn't an ambiguous number. By writing out the uncertainty, I tell you exactly where the sig figs are, right? So you can either, if you get a number like this, 2 sig figs, but it's 3 decimal places, we can't just write 250 minutes or it's ambiguous. We can write 2.5 times 10 to the 2 minutes. Either of these two is full credit. If you really don't like scientific notation and you really would rather take the extra time to write this every time, that's fine. That's not an ambiguous number, so that's a full credit answer. It's actually extra work though, once you get the hang of scientific notation. What if we're adding these two lengths? Similar figure, you've seen this figure before, right? What is our measurement for this first piece of wood? 4.56. I will say it's refreshing to teach a group of college students. I've been teaching this class at the high school the past couple of years. And the number of times the students are trying to shoehorn 6, 7 into every time I write a number is off the charts. 4.56 centimeters. Here, 3, but it's plus or minus a tenth, right? So 3.0. We're gonna add those two together. Your calculator answer is gonna be 7.56, right? But we don't get to keep all of those digits. So it would just be 7.6 centimeters would be the calculator answer, actual answer. Because this shows our uncertainty properly. So addition and subtraction, as long as you actually know what the uncertainty is and you're paying attention to this uncertainty, it's not too tricky. It kind of makes sense, right? I could be off by a tenth here, so my final answer could be off by a tenth. Multiplication and division is a little bit different though. Because those uncertainties compound on each other. So we're not actually going to just look at uncertainties. We're not going to look at uncertainties at all when we're talking about multiplication and division. When it comes time for multiplication and division, sorry, that's just working through all the stuff that I already drew on the board. Practice problems if you want. When we multiply or divide, the product has to have the same number of sig figs as your fewest number of sig figs. So however many digits were in your measured number before, that was how many sig figs you had. We're going to keep the same number of significant digits after the multiplication. We don't get to keep everything. So if we found the volume of a cube or volume of a rectangular prism, for being precise, I guess. Volume of that cube is length times width times height. When we plug these numbers in, we get a whole bunch of decimal places. Obviously, if we had our uncertainties in the hundredth of a centimeter, we're not going to actually be plus or minus 0.00001 cubic centimeters at the end. And we're not even going to be plus or minus in the hundredths place, like we were before, because all of those uncertainties build on each other. So when we multiply and divide, we're just going to count your fewest number of sig figs. So 4 sig figs, 4 sig figs, 3 sig figs. That means our final answer, we only get to keep 3 sig figs. So it's a little bit more complicated seeming, but it's actually simpler rule. I found it when I was first learning these rules. It's a lot easier to just count sig figs than to pay attention to the uncertainty. Counting the uncertainty makes more sense, but counting sig figs is easier. And that's kind of how I kept it straight in my head, is that addition and subtraction, the rule makes more sense. It's just looking at the uncertainties. Multiplication and division is more complicated, but the rule is easier. Count your sig figs, keep your smallest number of sig figs. Corbin?
Question, if, let's say that the volume was 1,550 and your smallest sig fig was still 3, would you then have 155 centimeters cubed.
So if it's 1,550 centimeters cubed and we're trying to keep 3 sig figs.
Yeah, would you just use scientific notation to move it up? But doesn't that kind of count as keeping an additional?
No, because this isn't a sig fig.
Okay.
Because we had to round to to 3 sig figs. If we're rounding 3 sig figs, that doesn't count anymore. It's just that 155 counts. So 1.55 times 10 to the third cubic centimeters. The other thing you can do when we start talking about units more, you can also change the units. Instead of saying that it's 1,550 cubic centimeters, you know that 1,000 cubic centimeters is a liter, you can just say it's 1.55 liters. By switching the units, sometimes you can get around having to use scientific notation as well.
Thank you.
Yeah, no problem. I'm gonna skip these practice problems as well. Other than what I would point out is that if you're following your rules properly, sometimes you gain a sig fig when you do addition and subtraction. Or you can lose a sig fig. If I wanted to say, if I had 9.52 feet plus 3.75 feet, both of those are 3 sig figs, right? But when you do the addition and you keep the uncertainty in the same spot, so that we're gonna keep our last digit in the hundredths place. Once we add them up, we're gonna get something that's 4 sig figs. So your number of sig figs can change on a number if you're following your rules properly. The opposite can be true as well. If we do subtraction, if I said, let's say I've got a sick kid at home. Let's say he has a 101.2 fever. And I want to know how much that is above 98.6. So I'm going to subtract 98.6. I had 4 sig figs and I subtracted 3 sig figs, and I'm going to get an answer that's only 2 sig figs. Right? So because it's going to give me, don't make me borrow why did I pick those numbers? 2.6, thank you. 2.6 degrees Fahrenheit. So it looks like I did lose sig figs. But that's the rule because that keeps the uncertainty in the same spot. Right, so knowing which rule to use is going to be one of the trickiest things in this class because it's a real pain to keep track of 2 different rules for rounding. But that's how we make sure we put the uncertainty in the right spot. All right. Those were left over. I thought I deleted those slides. If we have a change in the order of operations, that makes things more complicated. So let's say we're doing a calculation that has both addition and multiplication in it. Which set of rules do we use? Turns out we have to use both sets of rules. When we're multiplying, that's a bad. So I'm going to leave that one there as practice, but I don't like that problem. Let's say I want to look at the overall area of this classroom. We're just going to estimate it. We're going to make up numbers. What's the overall area of this classroom? Somebody throw out a number. What is the width of this?
25 feet.
I don't like feet though, so let's do it in meters.
12.52 meters.
Are you that sure about it? Probably plus or minus a meter, right? Let's call it 12 meters. And then how it's roughly square, right? So let's call it 12 meters deep too. Plus or minus a meter. What is that area then? 12 meters times 12 meters. 144 meters squared. How many sig figs do I get to keep on that? 2 sig figs. So 1.4 times 10 to the 2 meters squared. We have that nasty pillar right in the way. How much space do we have in this room without the pillar there? Or if we take away the space that the pillar is occupying? How big is that pillar? For the sake of simpler notes, so we don't want to use fractions either. It might be close to a quarter. I think it's closer to a half a meter, but fractions for quarter, what do you do for sig figs? Do you call that 0.25? Probably it is mathematically, but we don't want to write that because that's implying 2 sig figs. So let's call it 0.5 instead. It looks like it's about 1.5 feet. I think it's probably closer to 0.5 than a quarter of a meter anyway. We're going to subtract this area from our overall area. How many sig figs do we get after we find that area pillar? 0.5 meters squared, right? Which calculator wise gives you 0.25. But we don't get to keep both sig figs, do we? Now we're going to do subtraction. Once we do the subtraction, now we switch rules. We had to do both multiplications first, right? And then we do our subtraction. So 140 square meters minus 0.3 square meters. You're going to get roughly the same number back, right? Calculator answer is going to be 139.7 square meters. But we're already plus or minus 10 square meters. So within sig figs, that pillar occupies 0 space within sig figs. Basically, it's insignificant. We wouldn't actually say it occupies 0 space. We'd say it occupies an insignificant amount of space. We had to switch rules though. If we were just trying to do this all in one step on our calculator, we could type in 12 times 12 minus 0.5 times 0.5. Right? That's mixing our order of operation up though. We have addition, we have subtraction and multiplication in the same line. Means that's really hard to tell where to round it. Once we get our, that's going to give us the same 130, actually it's going to give us 144, 143.75 would be the actual calculator answer in that case then, right? How do we know where to round that though? This number is a lot harder to figure out how to round than if we stopped in the middle. So the point I'm trying to make here is that when you have a set of mixed operations, by which I mean multiplication and division and also addition or subtraction, you have to stop and do the rounding before you switch operations. Before you switch to doing the subtraction, you have to do the rounding for the multiplication first. Right? If you do it that way, that actually, it's more steps on your calculator then. But it'll keep you from making mistakes, because if we just looked at this, we'd say, I don't know, do I keep one sig fig? My 0.5 number only has one sig fig. Do I only keep one sig fig? It's hard. Do I keep all of them? What do I do? To avoid that situation, you stop. You hit enter on your calculator, write out your answer, do your rounding, and then do the second step. All right, it's a pain, but that's going to be the rule that keeps you from making mistakes. If all of your math, if you're doing a big long math problem that's all multiplication and division, you don't have to stop every step, because all of that multiplication and division is the same rule. It's the same order of operations in PEMDAS. If you're doing only addition and subtraction, you don't have to stop in the middle. You only have to stop in the middle and round when they're mixed together. If you're following all your rules properly, though, it shouldn't matter. You could stop every step of the way. If you had 5 multiplication problems in a row, you could stop after every step and round. And you should get close to the same answer within sig figs. By which I mean your last digit should only be off by 1 or 2, because that's where the uncertainty is. That's why we have rules for sig figs, is so that it doesn't matter if you wait to round at the very end or if you round every step, you should get close to the same number if you're doing it properly. There are extreme cases you can get really unlucky with that, where your last number is off by 5 in the last digit compared to, and I would have to pick the numbers very, very carefully. For the most part, those kind of cancel, averaging out. You'll round up half the time and down half the time, so it shouldn't make a difference. All right. Now that I've retaught you how to do addition and subtraction, we can do some practice. Let's do this one. This is a percent yield calculation. Percent yield basically means we're going to look at how much of the product we actually got, and how much product we were supposed to get, turned into a percentage. Actually, sorry, take that. This is a percent error calculation.
Just be sure those are the absolute value sign.
That's the absolute value sign. So basically, when we do a percent and percent error calculation, we don't care about which direction we're off. So we don't care if it's a positive or negative. We just care how far away you are from the real number. And then this underlined part means that's an exact number. How many sig figs does an exact number have? That's a different question. That's not a review question. Let's think about it. What does exact mean? Is it about 100%? No, it's exact. So it's 100.000 out to infinity, right? So infinite numbers, exact numbers have an infinite number of sig figs. There is no uncertainty in an exact number. So basically, if it's an exact number, it's not going to change your sig figs at all at the end. What step do we do first mathematically?
Well, yeah, subtraction.
Remember, with fractions, it's implied, like on the math review, it's implied that there's parentheses there. So we start with the parentheses. Everybody remembers. PEMDAS, please excuse my dear Aunt Sally. Parentheses, exponents, multiplication, division, addition, subtraction. For the sake of this class, though, multiplication and division and addition and subtraction are really the same step. right? Because subtraction is really just adding a negative number. And division is really just multiplying by the reciprocal. So they're the same step, but it still means we gotta do parentheses first. What do we get when we do this subtraction? Something point negative 0.011. Now, all that's left is multiplication and division, right? So we did our subtraction. If you wanted to write it out, 2.255 grams minus 2.266 grams. 0, -1 grams. Uncertainties in the thousandths place, right? So we're gonna keep the same number of decimal places. We're gonna keep the uncertainty in the thousandths place. So 0.011 is good. We don't need to do any rounding in this case. So now the final question is 0.011 grams over 2.255 grams. Absolute value. What does absolute value mean? Yeah, basically we take away a negative sign. If it's positive, it stays positive. If it's negative, we take away the negative sign. And then we're gonna multiply by 100% exactly. It really doesn't like that sign right there. Pretend I wrote a real percentage sign there. Now we're down to having sig figs, right? Now uncertainty doesn't matter because we're just doing division and multiplication. 2 sig figs there, which means our answer is only going to have 2 sig figs. We have 2 sig figs, 4 sig figs, and infinite sig figs. The 2 is going to control everything. It's also a good example. One bad number in a lab can throw out a whole bunch of work. If you work really, really hard to get a whole bunch of sig figs on almost all of your calculation, but you cut corners or you can only get a number with 2 sig figs in one spot, too bad. Your answer's got 2 sig figs. Doesn't matter how many sigs. We don't get to do something like, well, I had 5 sig figs there and 2 there, so I'm going to split the difference. Don't get to do that. Final answer here, what do we get?
You get 0.487804, but can't you just round it to 0.49?
0.48, you said?
Yes.
So yeah, we're gonna round to 2 sig figs. So there's our 2 sig figs. Sig fig rules still apply to percentages. How do we feel about this? Like we're ready for a break? Okay, we've been here for about an hour. It's time for a break. Let's come back at 25 after, and we'll talk about conversions after this. Talk about units more. Those are the fun ones. Conversions are actually fun.
That's the one I did.
We're gonna hammer conversions in this class. As conversions, you can use that to actually solve a lot of problems.
Oh, I wrote it down. That's
Wait, let's ask if this- So you have this.
Yeah, I'm nice, right? Gracias.
Oh, that's a mistake on my part. Let me log in Canvas. It's Canvas does this weird thing where if I import stuff from previous years, sometimes it keeps the dates, but it never does it properly.
Okay, yeah, sure. Also.
Yeah.
Yeah, exactly. Oh, that's fine.
But we don't get to keep those.
Yeah.
Yeah. Yes. Yeah, you can, so thanks for reminding me. I'll say this to everybody after break. But yeah, I'm gonna have everybody come today. Everybody is supposed to come today already, and I have another thing I have to do tomorrow. So, yeah, come today like we planned. And then from after this, it'll be Thursdays. So we can see if we can get enough people to transfer from the other, to give us some flexibility, but it might be something where we need to move around a little bit. But we'll see. We might have a little bit wiggle room,
Okay.
but I anticipate you're probably not the only one that's gonna have that issue because it's hard to be here 3 days a week, right?
Right.
So we'll see what we can do.
Okay. Sounds good. Thank you.
Thank you.
Oh, I have anatomy at 8 AM.
Okay. What's your name?
Joanne.
Joanna. There is a lab this week. For this, usually we're not gonna be able to switch back and forth between days of the week too much, but if you can stay today, are you scheduled to be in lab today?
What?
You know what section you're in? I don't remember seeing your name on Monday. I think you're in section 2.
I think so, I think she is.
So you're scheduled to be here today anyway.
Okay.
And then were you here last week? Okay. Okay, okay. So if what you missed last week was just a math review sheet, it's not due until the end of the day today anyway, and I have some printed copies. So you can work on that, or come to lab today like you're scheduled to, and I've got that copy for you. You'll be able to turn it in. Yeah, no problem.
But between just something as a. I have to talk. Was I get down everywhere else? Yeah. If I go to bed.
Okay.
So the spring I also do the. On top of ours.
Just do this before I lose that.
Yeah. I feel like that's so stupid. I mean, when it comes out, like, I feel like your coach, like,
Yeah.
he sees me. But said he like created, he's my class.
Mhm.
So he said, show you. He said, you're such a great.
Uncertainty is the last recorded number is your plus or minus 1. So the thermometer might read 101.2, it really could be 101. So when we say keep, that's what I mean when I say uncertainty. Every number that you write down in this class, if it's a measured number, it's plus or minus 1 in that last digit. So what it just means is keep the uncertainty in the right spot, means keep the same. Number in this spot.
Regular. Like, yeah, very good. Like, I felt every single day. Like. They just are.
Karen?
That's why. It's something. Yeah. It's nobody. The second one. Like going into detail about it. I heard she was like, like more point. Yeah, she was bringing up the. Yeah. Serious?
Some good guesses right now. Okay.
So we're gonna check, good to go on that. Thanks, awesome.
Thank you.
Yeah. And nutrition.
Oh, okay.
Like, it's just like.
Beatles.
No, have that. Sorry.
Yeah, I think.
He takes it.
Different music.
No, it's okay, I. Yeah. I love music. Going back.
Oh.
Yeah. Like the same like when it's just test, it's just not get it.
Yeah, I see.
Like,
Did you
that
take
was
the bike?
great.
Yeah.
Yeah.
Part of it was that when I went to grad school in Colorado, it was the craft beer boom, and there was lots of good breweries in California where I could get good beer for cheap, and so I got used to good beer, and then I looked at good beer was expensive, so I started making it. Part of it is just it's a cool system, especially if you're into biology and chemistry, it's really fun just to tweak the different variables and see what happens, change how dark it is, how light it is, how hoppy it is, flavors and hops, that's all stuff that flavor. And I thought that was really fun, but back when I didn't have kids and I was not the time, I had to be learning that. Buy nice beer, now I have no time, so now I buy nice beer instead of making it myself, but I still but yeah, it's a good hobby to get into, and it's a good field to get into. If you're into like microbiology, fermentation is a really subset of that has like real world applications, like making kombucha, working in the distillery, making sourdough, stuff like that is biology and it's also chemistry. So it's something that's kind of fun to do where you actually get to use science on an everyday basis. So make something fun to eat.
Yeah. Around graduation, too, I think.
That's it to go.
Multiplication division was the most here rule. So you guys look at the state fix, yeah. Addition and subtraction makes sense. It's the same uncertainty. Uncertainty. So like that's your friend, you keep the less aspect. So like if your friend driving here has plus or minus 10 minutes. And they're calling and tell you you're gonna stop at a traffic light, that doesn't add at any time, right? That's addition and subtraction, that's adding.
So adding that.
And getting stopped at the traffic light, yeah.
Add that.
Exactly.
Example of.
So, yeah, 250 minutes plus or minus 10 minutes. We're gonna add it.
Okay, so like radiology.
Plus or minus 1 minute. Yeah, 251. Minus 10. Still plus or minus 10. You keep the same certainty when you add.
They're watching.
It means you keep the same decimal place as your least. If this one goes to the 10th place, final number, I'm gonna go to the 9th place. Makes sense?
Going down the stairs, I'm like. Walking, I struggle. Not the move.
I know, I say the ESPN. Because if you pay for the blue line, it's ESPN,
Alright, quick announcement for our people that are on the wait list or interested in that Thursday lab section. I also mentioned we're starting that next week. So everybody's already planned on either coming to Monday or Wednesday this week. We're keeping that plan because I have something else. I have to go back to the high school tomorrow, finish up the class over there. So after this week, my Thursdays will be free. Well, not free, I'll be with you all, those of you who are in the Thursday lab section. But for this week, come to Wednesday lab section like we already planned, if you're on the wait list. Or whatever lab section you already talked to me about coming to. And if you can't come to Wednesday's lab section, talk to me after class and it'll be the same spiel that you give everybody else. If you can't come to a lab, you can get half credit for doing the write-up if you're not here. But anyway, so if you're not able to come today and you're scheduled to come today, talk to me about it. I know several of you sent me emails this morning letting me know that, but let's talk about it. That's a good call. Next week, we don't have a lab. Next week, so nobody has a lab next week because Monday doesn't have a lab, and it's not fair to make the Wednesday students come to class when Monday's not coming to class. That would get our schedule all skewed. So days when we have a Monday off, there's next week and then there's one in February. Nobody has lab those weeks. So everybody has next week lab off. Thanks for reminding me, Bianca. All right, let's come back and start talking about units some more and conversions. So you all have, for the most part, been doing unit conversions in your head to some extent for probably since you were old enough to do multiplication. I said earlier today when I said how many inches are in 6 feet. Most of you knew what to do to get that conversion off the top of your head, right? How do you get from feet to inches? You multiply by 12. Why do you multiply by 12? Because there's 12 inches in a foot. But mathematically, how does that work? Because we're going to start with some conversions that you know how to do intuitively. So that when you get conversions you don't know how to do intuitively, you can just follow the same process. So we're going to start by talking about what a conversion is, a unit conversion is. So anytime we write a number in a unit, if we can say it's equal to something else, we can call that an equality. An equality mathematically just means you've got an equal sign in there somewhere. In the sciences, that means that you're saying two things that might have different units are equal to each other. So for instance, 1 meter equals 100 centimeters, or 12 inches equals 1 foot. Those are both equalities. Once we have an equality, we can do algebra to it, which sounds scary. This is kind of a simple thing. What do you mean I'm going to do algebra to that? That sounds intimidating. I just mean that we can, anything we do to one side, we can do to the other side. So we can say things like, I already had it written. We can say that, okay, I'm going to divide both sides by 1 foot. If I divide both sides by 1 foot, that doesn't look like it necessarily helped me do anything. What happens to the right-hand side of that equality? It goes away. Well, it turns into 1, right? So everything cancels out, equals, so we have 1 equals 12 inches over 1 foot. Weird, but sure. Why would I bother doing that? Because anytime we have 1, you can multiply anything you want by 1 without changing that number, right? Well, that also means, so here's an example. We did the same thing with meters and centimeters. If we're gonna multiply by 1 without changing the number, we can also multiply by anything equal to 1. Like a conversion factor, sorry, I didn't define that term. This is called the conversion factor. Once we do that, and we say, okay, this ratio is equal to 1, we're gonna give that a new name. It's really kind of like an equality, except it's an equality written as a ratio. So we call that a conversion factor. If a conversion factor is equal to 1, that just means, the other way to think about that is that just means the top of a fraction equals the bottom half of a fraction. Anytime the top of a fraction equals the bottom of a fraction, it is a conversion factor. So if we want to convert from, we'll stick with feet and inches real quick. Our conversion factor was 12 inches over 1 foot equals 1. If we want to convert 6 feet into inches, all we're going to do is we're going to say, okay, I've got 6 feet. I'm going to multiply by a conversion factor, but I'm going to pick the conversion factor so that the unit that's on the bottom of the conversion factor is the same as the unit that's on the number we're starting with. So if I say 1 foot is equal to 12 inches, I just multiplied by 1. So no, I didn't change the number. But I did change the units, because now what happens with these feet? This is really over 1, right? It's when we multiply fractions, we just multiply straight across. So when we do this, we're gonna get 72 feet times inches over 1 foot. So what happens to feet? It cancels out. Basically, when we're dealing with units, units behave a lot like variables in terms of algebra. So if you have the same unit on top and bottom of a fraction, you can cancel them out. So feet cancels with feet, we're just left in inches. All we did was multiply by 1, but we changed the unit. So that's the heart of what a conversion is we're multiplying by 1. We're just writing 1 in such a way that some units cancel out along the way. So if we're trying to go from meters to centimeters, again, this is another one that most of you probably could do in your head. You know what the step is to go from meters to centimeters, right? What is it? Meters to centimeters, not meters to feet. Multiply by 100, because 1 meter equals 100 centimeters. Which means we can rearrange these so that we say, okay, well, that means 100 centimeters over 1 meter equals 1. The top and the bottom of the fraction are equal to each other. When the top and the bottom are equal to each other, we could multiply without changing the number. That's the heart of doing this. And then the other step to remember is that we want to cancel out that meter. We're trying to get rid of meters because we want to end up in a different unit. So we're trying to end up in meters. We're going to take 0.571 and we're going to multiply by that conversion factor. We're going to put 1 meter on the bottom so that meters can cancel out with meters. And then we just have to put something equal to meters on the top. 100 centimeters. Meters cancels meters. 0.571 times 100 divided by 1 gives us 57.1 centimeters. Right? Levi?
Could we just move the decimal point twice?
You can. And that's one of the advantages to using those metric prefixes is that they're all even powers of 10. So you can do it that way. What I find is that when it's an easy one like centimeters to meters, sure. But when if I start saying something like, okay, go from kilometers to nanometers, that's trickier, right? So it's when in doubt, show your work so that you know you're not messing it up. The other thing that people run into is if you try to do too much in your head, people will divide by 1,000 when they were supposed to multiply by 1,000. If I say go from kilometers to meters, they'll wind up going the wrong direction if you're not showing this. The other thing I will also say that goes along with that is make sure that you don't do something silly, like say 100 meters is 1 centimeter. Probably 10% of you will do that on one of the tests, or will do that on the final. Because we are in a time situation, it's really stressful. It's really easy to say, oh, I know that there's 100 centimeters in a meter, and then write it as 100 meters over 1 centimeter. We know that's not true, right? I know that my students know that that's not true when they write it on the test, but that means that you're going to get the wrong answer if you do that. So when you're writing these conversion factors out, just make sure you don't do something, make a dumb mistake like that. I say dumb mistake, it's a dumb mistake, not saying that you are dumb if you make that mistake, right? It's easy to do on a test when you're trying to go as fast as you can. And like I said, it happens every year. All right, so that's easy enough when we already know what we're trying to do. Feet to inches, we already did an example with that, right? We're going to set it up so that feet is on the bottom, 12 inches is on the top, and multiply across. What if we wanted to do 5.33 times 10 to the 6 inches into miles? How do you go from inches to miles? This is why we start with the easy ones to warm up. Do we have a conversion? I don't have the conversion sheets printed for you all yet, but is there an easy conversion that you know off the top of your head for inches to miles?
Step through feet soon.
Yeah, we don't have a conversion for inches to miles, but we do have a conversion for inches to feet. And we do have feet to miles. Yeah.
1,600. So.
You're close. This is why we have a conversion sheet, right? You don't have all these memorized yet. 1 mile is 5,280 feet. There's 1,600 yards in a mile. Are you a swimmer or a runner?
I used to run track. I was for some reason thinking that 400 feet was 1 mile, but that's just 1/4 of.
That's a quarter of a mile,
Yeah. Yeah.
So if you are on the swim team in high school and you get in trouble with the coach and he makes you swim the mile into your next swim meet, like happened to me on occasion, then you're swimming 1650 which winds up being 42 laps, I think. Don't make your swim coach mad if he's setting what races you're in the next meet. Basically, is the lesson there. In my defense, he was going to put me in that anyway. All right. If we know that we can get from feet to miles, and we know we can get from inches to feet, we can just do this in 2 steps. And so I'm just going to blank this out so I have space to work. If I can go from 5.33 times 10 to the 6 inches, and I can convert that into feet, because we already know how to go from inches to feet. Well, once I'm in feet, I can go from feet to miles. So basically, it can be an advantage in some of these conversions. This is not the last time you're going to see a conversion that takes multiple steps. it can be an advantage to plan it out. As long as you know that you've got a conversion for inches to feet and you know you've got a conversion for feet to miles, this isn't too tricky. What's our conversion for inches to feet?
Make it right conversion back.
Write it as a conversion factor, so we want inches on bottom. This is writing it out as a conversion factor is how we make sure we don't multiply by 12 when we're supposed to divide by 12. There's 12 inches is 1 foot. So we're gonna be dividing by 12. And that'll give us a number. Something times 10 to the 5, right? Something like 4.8. Four point two, maybe. Somebody correct me. 4.4? How many sig figs do we get to keep though? So 3 sig figs there. What about on this conversion? Is it about 12 inches in a foot? It's exact. If our conversion factor is exact, it's not going to factor into how many digits we get to keep. So if this is exact, we started with 3 sig figs, we still get 3 sig figs. So 4.4, 4. Times 10 to the 5 feet. Now we're in feet, as long as we know what the conversion factor is for feet to miles. Which I wrote it on the other slide that you can't see now, but it's 5,280 feet is 1 mile. You don't have that one memorized, don't worry. I'm never gonna ask you to do conversions without your trusty conversion sheet. So you wind up memorizing the easy ones anyway, because you're gonna use them a lot. But your periodic table and your conversion sheet, I call that your safety blanket in this class. I'm never gonna take away your safety blanket. Other than the one in-class quiz where I quiz you on atomic names and symbols. There'll be one quiz. It'll only be 20 minutes long. Other than that, you always have your safety blanket. Okay? So we're gonna divide by 5,000. Roughly speaking, what should my answer be? You're doing this in your head, you're just trying to get a rough idea. This is 44,000. Sorry, 440,000. Divided by 5,000. Something in the hundreds range? Or 80 maybe?
84.1.
I didn't do that mental arithmetic. As I said it in my head, as I said 100, I remembered this problem from last year. So it's not too tricky, but if I just said convert from inches to miles, that's not when you know how to do intuitively, right? So showing your work is going to be what gets you from point A to point B. Make sure that you're canceling the units out properly. Whatever unit you start with goes on the bottom of your next conversion, so it can cancel out. If all of our steps are multiplication, did we need to stop in the middle? From a mathematical point of view, from a logic point of view, and an understanding point of view, perhaps. But mathematically, did we really need to stop and hit enter here? No, because we just took the answer there and then multiplied it again or divided again, right? So you can actually write these all in one line. And you should get the same answer within sig figs. So 5.33 10 to the 6 inches. 12 inches is 1 foot. And 5,280 feet is 1 mile. Same 2 steps, right? And inches still cancels inches and feet still cancels feet. And I would wager for this one, it's gonna be the same number after you route. If this looks intimidating or confusing to you, if you didn't understand what I did that second step, just stop after every step. Do your conversions one at a time. There's nothing wrong with that. It'll just take up a little bit more time and space on your paper. That's totally acceptable. You will still get the right answers. All right. So now you know conversions. You're all experts in conversions now, right? I won't expect it to go that fast. Don't worry. Yeah.
Can you explain one more time why you went from 10 to the power 6 to 10 to the power 5?
Because when you take this number and you divide by 12, this is what your calculator spits out. I knew it was gonna be to the power of 5 because that 12 is kind of like 10, right? If I'm doing mental math, I'm gonna just call 12 10. If I'm taking this number and dividing by 10, that's gonna switch it from 10 to the 6 to 10 to the 5. But if you're not doing that in your head, just plug it in your calculator, you should still get that 10 to the 5 answer to come out. Anybody else? Anything I did that was too fast or didn't make sense? Any arithmetic errors on the board? Usually find the fastest way to get people to speak up is when I make a mistake in the math on the board. So feel free to correct me. I want you to correct me if I get it wrong. I don't want. And even if you're not sure I got it wrong, but you think I got it wrong, ask about it. All right, let's do. Let's do some other conversions. I'm gonna pull up the conversion sheet and I'm gonna write some practice conversions on the board. We're gonna practice using those prefixes now. All right. We're gonna do two conversions that are simple. Ish. And 2 that are a little bit longer. Let's go. Let's go from. We'll do 5.0 kilometers into. We'll keep into feet. And we'll do. We're gonna do 7.50 minutes into years. Then we can do 85.7 kilograms into pounds. And let's go 752 nanometers into inches. So I'll give you about a 5-minute head start, talk to the people around you, and then I'll start working through these. If you have your computer, you can pull up the equation sheet from Canvas. It's on, go down to resources at the bottom of the homepage. And there's a link to the conversion sheet there.
And then 1 meter.
Minutes. There's a mile. Over yard. Why? That actually. Oh, it's been 5 years. No, it's been years. I could do this, right? Because there's more shades there. 60 minutes. It's from, it's really. No, but like we did 7.
So that's what you said is sufficient. Yeah. That's me, right? So I said, Walker. It's 15 hours. We just have 7 issues. Hours. We have 7 minutes. Multiply that by 6. And that's really well. Yes, yes, and then
Well, I haven't done that, I'm playing right now.
It says all these. When don't really take one. So that is all. You know.
You went too small.
Those.
I just don't want to choose. Yeah. Wow. I mean, yeah, but I have. Yeah, you would.
That's my number one.
No safety.
Yeah, and they go 5 million, that's why I'm not. That's what he said. Yeah.
I guess we have to look at it. Bottom.
Yeah.
Apply it from 5.55.
No matter what, you're saying. That's what I said. Did you think the person would put 5 million?
Just a reminder about the math, if you're doing one of these longer conversions, if it's on the top of the fraction of the conversion factor, you're multiplying by that number. It's on the bottom, you're dividing by that number.
Why before you just write it on it? Well, that's not, I thought like it says. Another position.
You're doing this, Bianca? It's on the bottom of the fraction, right? You divide and then divide again. It's okay, that's why we're practicing. Technically, you're multiplying all of them. You're gonna multiply it across, but 1 times 1 is 1.
Okay.
And it would just be somewhere. Yeah, right. Because then a mile, like 1 mile, this feet. Well, this is.
All right, I'm gonna clear the conversion sheet so I can work on the board, so it'll be on the recording. You still have a conversion sheet pulled up, you can keep working if you're not done yet, but I'm gonna start the top left and work my way to the right.
On canvas. And then the.
Well, like I was reading out, whatever, yeah. So this is.
So I like this first one as an example of, this is a conversion where there's two equally correct routes. Actually, arguably the second route is better. Because if you use the second route, you can use all exact conversions and keep all of your sig figs. Because if you look at the conversion sheet, your conversion from kilometers directly to miles is approximate. It's got 4 sig figs, which is usually enough. But if you really wanted to keep all of your sig figs, then you might want to go the long route here. But both of them should give you the same number. Do 5.0 kilometers. And for every 1.609 kilometers. 1 mile. So you should get something like 3.1, I think. If my running memory is correct. Then you can go from miles to feet. 1 mile is 5,280 feet. So we should get something in the 15,000 range. Maybe 16. 1.6. So what's the calculator answer?
15,407.7.
407.7. The calculator answer spits out this, or something close to it, depending on if you round it in the middle or not. We only get to keep 2 sig figs though. We have 2 sig figs on our starting number. This is not an exact conversion, as noted on your conversion sheet, so we have to think about it. It's not infinite sig figs, but it's 4 sig figs. So 2 sig figs, 4 sig figs, this is exact. Any of these conversion factors that are within the same system, meaning you're going from imperial units to imperial units, like inches to feet to miles, those are exact. Any of your conversions that are metric conversions to other metric units are also exact. There's only one exact conversion though to go from imperial units to metric. And it's this one. Right, so if you want to use only exact conversions, you have, and you're talking about length, you have to go through centimeters and inches. Doesn't matter in this case because I only gave you 2 sig figs to work with anyway. So our final answer is it's 16,407.7 feet. We're gonna round it to only 2 sig figs though, so 16,000. We don't want to write 16,000 though, because that's what type of number? It's not exact, it's ambiguous. Throwing around all these different types of numbers. At least we're not getting into irrational numbers. 1.6 times 10 to the 4th feet. If you went the long route, again, should give you the same number within sig figs, especially in this case, since we're only keeping 2 sig figs anyway. But it would look like 5.0 kilometers,
So what's 6?
1 kilometer, 1,000 meters. 1 meter, 100 centimeters.
That's like to the fourth.
2.54 centimeters. 1 inch. Exactly. It didn't used to be exact, but it used to be, if you look at the original definition of meters and inches, it was something like 2.54002 centimeters was 1 inch. So at some point in the 80s, I want to say, the US just redefined what an inch was to be exactly 2.54 centimeters. Nobody even had to buy new rulers because it was already such a small amount that it was off that didn't really make a difference to anybody. But what the practical upshot is that we can now say that has infinite sig figs. That's an exact conversion. And then we can go inches to feet. I would not have expected anybody to go this route at this point. I wouldn't have gone this route necessarily unless I was dealing with something that had a whole bunch of digits. If I had a whole bunch of sig figs and I wanted to keep all of them, if I had 5 sig figs, I don't want to use this conversion because then I lose one of my sig figs that I worked so hard to measure. So if I had 5 sig figs and I want to keep all of them, I would have to go this route. For this problem though, doesn't make a difference. You did get the same number, right? All right, questions on this one? Anything that I did that didn't make any sense? Okay, let's do minutes to years. What's our roadmap gonna be? What conversions can we do? We could go from minutes to seconds and then seconds to hours, because that's on the conversion sheet, but that's kind of going backwards, right? You just go minutes to hours. I think that one should also be on there, and if it's not, we know it. Hours of days. You could go days into months, but then how many days do you say are in a month, right? If you check your conversion sheet, there is a conversion that goes straight from days to years. You should, because if you go from minutes to seconds, you're gonna multiply by 60 and then divide by 3,600. Which is the same as multiplying by 60. Or same as dividing by 60, I mean. You just wanted the practice.
Yeah.
So 60 minutes is 1 hour. 24 hours is 1 day. And 365.24 days is 1 year. Be a small number, right? Makes sense. 7 minutes is not a very big chunk of a year. What is this 0.24 about? Leap years. What's a leap year means we get an extra day every 4 years, right? So every 4 years, the 0.24 adds up to about another day. So if it's not 0.25, if it was 0.25, it'd look pretty exact that way, right? Turns out the calendar was not designed properly. I guess you could put it that way. It would be really convenient if we defined our calendar such that a whole number of days was exactly 1 year. Turns out that's not how orbital mechanics works. And we can't really control the rotation of the Earth or how long it takes us to make our way around the sun. So we're stuck with this. And every 100 years, this number is off by a day. Because adding a leap day every 4 years is assuming this is exactly 0.25, and it's not. It's every 100 years, you get it, that extra 100 there adds up to a whole day. So every 100 years, we don't have a leap day. So normally on years that are divisible by 4, we have a leap year. We have a leap day added, February 29th, right? Except not on the year 2000. The year 2000 and the year 2100 will not have leap days, even though it's divisible by 4 because of that extra decimal point there, or that extra missing 100th of a day. So is this an exact number then?
No.
So we do have to think about it in terms of sig figs. This is good enough. If we just use that system I just described for leap days, we might be off by a day every 1,000 years. I don't think anybody's keeping, I shouldn't say that. I know somebody's keeping track of it that closely, but it's not me. So somebody 1,000 years from now will tell us, oh, we have 2 extra leap days because of these extra sig figs that are past the 4 here. All right, so final number, what do we get? This is also a good point or a good time to bring up. Don't start making up your own abbreviations for units. It seems like they're just kind of willy-nilly, but especially units that start with M. There's a lot of units that start with M. You can't just say MI for minutes. Because what's MI? Miles. You can't just say M for minutes because what's M? Meters. Turns out we are even gonna start getting picky about capitalization in units. Capital M does not mean the same thing in a unit that lowercase m does. So you have to actually be pretty picky about the way you write your units to make sure you're not gonna confuse people or confuse yourself. If you try to write minutes as miles, you might start trying to convert 7.5 minutes into kilometers if you're not careful, right? So let's pay attention to that. All right, questions on this one?
Is it 5? I miscounted, it's 5.
5. Oh,
Yeah, I did 5. So smart.
Okay.
Like and then like big.
Minus 5. So here's another good note about the way that I grade these. These are the same number within sig figs. Because 1.42 is it, we're assuming that's plus or minus 1 in the last digit, right? So if you messed up your rounding, as long as it's still within 1 of what it's supposed to be, that's the same number. Because you could have, if you stopped and rounded after every step, you could be off by more than that. A little bit. If you follow your rules for rounding, you shouldn't be off by that much. But it's always plus or minus 1 in that last digit. So as far as I'm concerned, those are the same number. And so anytime you hear me say it's the same within sig figs, that's what I mean. I mean, it's within the uncertainty that we already have. All right. Let's do kilograms to pounds. So this is a good problem. First off, anybody know why the abbreviation for pounds is LB? What is pounds in Spanish? Where did that come from? From Latin. So most Latin-based languages have a very similar word for pounds. English just has to be difficult. And so they use the word pound, but the abbreviation from the Latin. So, do we have a conversion for kilograms to pounds?
Yes.
Is there one directly on there?
Yeah.
Oh, dang. Let's pretend that's not there. We have to go through grams first. The one that I know off the top of my head is grams to pounds.
Yeah, because it's backwards.
If we're trying to get to pounds,
When does zero start first?
if we only have one conversion, to get from pounds, to get to pounds, we know we have to go through grams to get there. So sometimes when we're writing out these roadmaps, it can be helpful to start at the end and work your way back, because sometimes you only have one conversion available. If you only have one conversion that gets you to the units that you want, you know you've got to use that conversion. Which means you've got to work backwards. And then you can say, okay, well, if I know I have to go through grams, which again was not the case here, but I meant for it to be the case. I know I can go from kilograms to grams, and then I know I can go from grams to pounds. So 85.7 kilograms. I also was trying to force you to use those metric prefixes. How many grams are in a kilogram? 1,000. Because the multiplier on your conversion sheet is 10 to the 3. So a kilogram is 1,000, is 10 to the 3 times larger than a gram. So for every 1 kilogram, that's 10 to the 3 grams. Or 1,000. When we're dealing with these prefixes, I usually am just gonna write my conversions like this because it's a lot easier to do that than it is to write out 1, 0, 0, 0, 0, 0, 0. If we're doing, you know, to a millionth power, it's a lot easier to write 10 to the 6. Then we can use our grams to pounds. 453.59 grams, 1 pound. So we're gonna multiply by 1,000, then divide by 450. Gonna be something like 200, right? So how many sig figs do we get to keep? 3. 3 sig figs, infinite sig figs, 5 sig figs. So any of these approximate sig figs, I guess I should also say these ones are exact. It's the measured numbers that show up down here with all the decimals. That's where you're counting your sig figs. We're saying exactly 1 pound is about 453.59 grams. So that's measured, that's exact. Otherwise, they would all look like they have only 1 sig fig. All right. Last one. 752 nanometers, which is roughly the wavelength of red light. And we want to put that into inches. No getting around using the prefixes on this one. We're trying to go from nanometers to inches. What are we going to go through? You go nanometers to centimeters. But to get to centimeters, we're going to need meters. So again, if you're working backwards, there's only one conversion to inches from metric, and it's centimeters. So 752 nanometers. So the conversion sheet says, it says nano. Then underneath that it says N. Then underneath that it says 10 to the minus 9. What does that mean?
1 meter is a billion meters. Wait, yes, nanometers.
It means to get to to 1 nanometer is 10 to the minus 9 meters. I don't like thinking in negative decimal or negative exponents if I can help it. And so you could say 1 nanometer equals 10 to the minus 9 meters. That's a valid conversion. I don't like that though. I think about it the other way around. And I say 10 to the 9 nanometers equals 1 meter. They'll give you the same answer. It's all personal preference. I think about it this way. That's how I'm going to write my conversion factor. But if you use this version of it, even better. So we can say for every 10 to the 9 nanometers, because we know a nanometer is small, so it takes a lot of them to make 1 meter. Then we can say 1 meter with 100 centimeters. Did you combine those two? Yeah. if you're really good at carrying exponents in your head and you wanna try and combine those into one conversion factor, fine. I always do it this way because I don't trust myself not to multiply by 1,000 when I was supposed to divide by 1,000. So I always write it out this way. And then we can use our 2.54 centimeters is 1 inch. So looking at this, are we gonna get a really big or a really small number? Small, nanometers are really small, right? So even though there's 750 of them, we're gonna divide by a billion, then multiply by 100, then divide by 2. It's gonna be a pretty small number. Comes out to be what? So 0.0000296 inches. Pretty small. Smaller than we're measuring with the ruler. Say that. All right, how do we feel about conversions? Got a little bit of practice. We're gonna get lots of practice. We're basically gonna start every class is gonna start with a conversion practice from here on out. Because we're gonna use it for pretty much everything. This is gonna be your number one tool that you use in this class. It's gonna be conversions.
Is it common in research to fiddle around and find a good chain of conversion to maintain or measurement type?
To some extent, once you get used to it, it's kind of second nature.
Okay.
And if you're working in research, odds are you're looking at the same units all the time.
Oh,
So you just wind up having like, okay, I know what my pathway is for this particular.
My second question is kind of like, why don't they just report the original unit if they wind up doing the same thing? So.
Because some units are easier to use than others, and sometimes you're actually stuck based on what your equipment is. If your equipment is in, I don't know, inches of mercury for pressure, you're not gonna go buy a whole kilometer just because inches.
That makes sense. Okay.
If I would, so now we were filming this. So, the size. Last.